Our galaxy holds secrets that defy everything we think we know. We are about to embark on a journey through the 25 most baffling mysteries of the Milky Way, from the invisible grip of dark matter to inexplicable radio signals from the void. By the end, you will see our home galaxy not as a familiar spiral of stars, but as a realm of profound and unanswered questions. We will investigate what colossal force is pulling us through the cosmos and why a strange energy haze surrounds our galactic center. What single cosmic mystery do you find the most compelling? But the biggest mystery of all is the one we cannot see. It is the ghost in the cosmic machine, a substance so elusive it makes up the vast majority of our galaxy's mass yet remains completely invisible. This is the enigma of dark matter. Think of our Milky Way as a colossal spinning pinwheel. According to the laws of gravity, stars on the outer edges should be moving much slower than those near the bright center. But that is not what we observe. Instead, stars far from the galactic core orbit at nearly the same speed as those closer in, as if something unseen is providing an extra gravitational grip, holding the entire structure together. That something is dark matter. Its presence is felt everywhere. We detect its shadow through a phenomenon called gravitational lensing, where the immense gravity of this invisible stuff bends the light from distant galaxies, warping their images like a funhouse mirror. We can map its distribution. We can calculate its overwhelming influence. We know it constitutes roughly 27% of the entire cosmos. Yet after decades of searching with the most sensitive detectors ever built, we have no idea what it actually is. It does not emit, absorb, or reflect any light. It simply is a cosmic scaffolding woven through the voids between stars, the greatest unsolved puzzle in all of modern physics. But if dark matter is the ghost holding our galaxy together, then the great attractor is the phantom pulling us relentlessly toward our doom. Our entire Milky Way, along with countless neighboring galaxies, is caught in a cosmic current, racing at over 1 million miles per hour toward a specific point in the distant darkness. This is not a gentle drift. It is a violent river of motion, all directed toward a mysterious gravitational heart we call the Great Attractor. Its location lies in the general direction of the constellations Centaurus and Hydra, a region of space that should, by all accounts, be unremarkable. Yet something with the mass of tens of thousands of Milky Ways is sitting there, a gravitational anchor reeling in everything in its vicinity. For decades, its true nature remained hidden because it lies directly behind the crowded plane of our own galaxy, a region astronomers call the zone of avoidance. Imagine trying to see a distant city by looking straight through the dense smog and bright lights of your own downtown. That is the challenge. The dust, gas, and blinding stars of the Milky Way's core completely obscure our view, creating a cosmic blind spot that concealed this colossal anomaly for years. So what is it? Early theories suggested it was a massive concentration of galaxies, an immense supercluster whose combined gravity was the source of the pull. More recent observations, using telescopes that can peer through the galactic dust with infrared and radio eyes, have revealed part of the truth. There is indeed an enormous supercluster there, called the Norma cluster, but its gravity alone does not seem sufficient to account for the immense force we feel. This has led to even more exotic ideas. Perhaps the Great Attractor is not a single object, but a node in the cosmic web, a point where the filamentary structures of dark matter and galaxies converge, creating a gravitational sink of unimaginable scale. It is a stark reminder that we are not still, but passengers on a galaxy hurtling through space, drawn by a force we are still struggling to see. This unseen river of motion, pulling our galaxy toward an unseen horizon, is mirrored by another, equally colossal structure that erupts from our galactic core. Two vast orbs of searing energy, known as the Fermi bubbles, balloon out from the center of the Milky Way. They are immense, each one stretching an astonishing 25,000 light-years into space, one rising directly above the galactic plane and the other plunging deep below it. Together, they form a ghostly hourglass figure that dwarfs every star in our sky, a structure so large it could contain entire galaxies. We only discovered them in 2010, when the Fermi Gamma Ray Space Telescope scanned the heavens and noticed this faint but gigantic haze of the highest energy light, gamma rays. It was like finding the ghostly imprint of a titanic explosion that no one had witnessed. So what could have created these colossal bubbles? The leading theory points an accusatory finger at the supermassive black hole sleeping at our galaxy's heart, Sagittarius, a star. Astronomers theorize that millions of years ago, this slumbering giant might have awoken in a violent feeding frenzy, devouring a huge cloud of gas and dust. Such a meal would not be quiet. It could have triggered a cataclysmic belch, a pair of jets, or an outflow of incalculable power that shot perpendicularly out from the poles of the black hole, inflating these giant bubbles with ultra-hot, magnetized gas. An alternative idea suggests a different kind of eruption, not from the black hole, but from a frenzy of star birth. In the crowded galactic center, a wave of intense star formation could have created thousands of massive stars that lived fast, died young, and exploded as supernova. The combined fury of all these stellar deaths might have blown a giant, superheated wind straight up and out of the galaxy, carving the bubbles we see today. The true answer remains elusive. We still do not know exactly what event caused this, or the precise nature of the high-energy particles trapped within these colossal structures, making them one of the most dramatic and unresolved features of our galactic home. From the colossal energy structures above our galaxy, we plunge into the heart of a mystery measured in milliseconds. Fast radio bursts are among the most fleeting and powerful phenomena in the cosmos. These are not gentle signals. They are violent, intense flashes of radio waves that erupt with the power of 500 million suns, yet they last for less time than the blink of an eye. For years, every single one we detected came from far beyond the Milky Way, from galaxies millions of light years away. Their incredible distance made their sheer energy output almost incomprehensible. Then, in April 2020, something changed. For the first time, a fast radio burst was detected originating from inside our own galaxy. This was a game changer. The source was traced back to a known object within the Milky Way, a highly magnetized neutron star called a magnetar. You can think of a neutron star as the collapsed, ultra-dense core of a giant star that went supernova. A magnetar is a neutron star on steroids, boasting a magnetic field so powerful it could erase your credit card from 500,000 miles away. When this particular magnetar had a starquake, a sudden adjustment of its crust, it released a blast of radio waves that we detected as an FRB. This discovery provided the first solid clue, strongly suggesting that at least some of these cosmic firecrackers are born from the violent tantrums of these extreme stellar corpses. Yet the mystery is far from solved. The sheer variety of fast radio bursts leaves the door open for other, more exotic origins. Some burst only once and are never heard from again, while others repeat in unpredictable, frantic patterns. Could there be multiple cosmic engines capable of producing these flashes? Some scientists speculate about cataclysmic events like the collision of two neutron stars or material falling onto a black hole. And yes, the idea of advanced alien technology has been floated, a possibility that, however unlikely, cannot be entirely dismissed until we have a definitive natural explanation. The true challenge in solving this puzzle lies in their nature. They are incredibly brief and utterly random, appearing anywhere in the sky without warning. Our telescopes have to be looking at exactly the right place at exactly the right millisecond to catch one, making the hunt for their true origins one of the most frustrating and exciting chases in modern astronomy. Deep within the heart of our galaxy, a strange and persistent glow defies easy explanation. While the Fermi bubbles tower above and below, the very core of the Milky Way emits a mysterious excess of high-energy light, a fog of gamma rays that should not be there. Astronomers call this the galactic center GVXS. Imagine turning on a powerful telescope and pointing it toward the crowded center of our galaxy, expecting to see the combined light of known objects like pulsars and supernova remnants. Instead, you detect a faint, diffuse haze of gamma radiation that blankets the entire region, a signal that does not match any of the usual suspects. The puzzle is not that there is light, but that there is too much of it, an unexplained surplus of energy with no clear origin. For years, the scientific community has been divided on what creates this anomalous glow. One compelling theory points to a vast, unseen population of ancient stellar corpses. These would be millisecond pulsars, which are neutron stars spinning hundreds of times per second, acting like cosmic lighthouses that beam out radiation. The idea is that the galactic center is so densely packed with stars that thousands of these faint, spinning pulsars could be hiding there, their individual signals blending together into a single, uniform haze that our current telescopes cannot resolve into distinct points of light. It is a chorus of faint voices that we hear only as a collective murmur. Yet there is another, far more exotic possibility that sends a thrill through the world of physics. This mysterious glow could be the first indirect evidence of dark matter itself. The theory goes like this. If dark matter is made of theoretical particles called WIMP, weakly interacting massive particles, then they should be densely concentrated in the galactic core where gravity is strongest. Occasionally, these particles might collide with one another, annihilating in a flash of energy that produces the very gamma rays we see. In this scenario, the haze is not from stars at all, but the ghostly afterglow of the universe's most elusive substance destroying itself. The debate is intense because the implications are profound. If the pulsar explanation is correct, it reveals a fascinating new aspect of our galaxy's stellar population. But if the signal is from dark matter, it would be one of the most monumental discoveries in the history of science, finally giving a face to the invisible entity that shapes our cosmos. For now, the strange glow at the center of our galaxy remains an open question, a cosmic tug-of-war between a crowd of unseen dead stars and the potential signature of the universe's greatest ghost. 72 seconds, that is all it lasted. On a quiet August night in 1977, a radio telescope known as the Big Ear was silently scanning the sky as part of the search for extraterrestrial intelligence. Its routine was suddenly shattered by a signal so powerful and so peculiar that it defied all natural explanation. It was a narrowband radio blast, precisely the kind of signal scientists had predicted an advanced civilization might produce. It was 30 times stronger than the background noise of space, and it came from a seemingly empty patch of sky near the constellation Sagittarius. The astronomer who discovered the data printout, Jerry Amon, was so stunned he circled the alphanumeric code representing the signal's intensity and scribbled one word in the margin. Wow, that single word gave the phenomenon its famous name, the wow signal. For 72 glorious seconds, it blared into existence, and then, just as suddenly as it appeared, it vanished into silence. It was never heard again, despite decades of searching with more powerful instruments. That specific patch of sky has remained stubbornly quiet, so what was it? The hunt for an answer has spawned countless theories. Some suggested it was a secret military transmission or a signal bounced off a piece of space debris. Others pointed to a passing comet, arguing its hydrogen cloud could have generated the burst. Yet the comet explanation was later debunked, as the celestial body in question was not in the right part of the sky at that exact time. The signal's unique properties, its narrow frequency and its intensity, continue to resist all mundane explanations. For a brief moment, it seemed we might have received a cosmic hello. Its enduring mystery serves as a haunting reminder of the profound silence that otherwise greets our efforts to find company in the cosmos, a single, brilliant question mark etched against the stars. While the wow signal hints at a universe that might be trying to speak, the cosmos is also filled with silent, drifting ghosts. Rogue planets are dark, nomadic worlds that wander the interstellar void completely untethered to any star. They do not orbit a sun, they do not experience day or night, and they are not warmed by a nearby stellar furnace. They are simply alone, adrift in the eternal cold of deep space. How does a planet end up so utterly lost? There are two primary paths to this solitary existence. Many are likely ejected from their home solar systems during the chaotic gravitational dances of their youth. When young planets jostle for position, one can be flung out by its siblings, sent careening into the galactic darkness like a ball from a cosmic pinball machine. Others might form all on their own, condensing directly from small, cold clouds of gas and dust too meager to ever ignite into a star. These lone worlds are born into isolation. Finding them is one of astronomy's greatest challenges. Since they emit no light of their own and are not illuminated by a star, they are effectively invisible to traditional telescopes. We detect them only through a clever trick of gravity known as microlensing. When one of these dark wanderers passes directly in front of a distant background star, its gravity acts as a tiny lens, bending and briefly magnifying the star's light. For a few hours or days, that faraway star appears to mysteriously brighten, then fade, revealing the presence of the invisible planet that crossed its path. It is a fleeting signature, a ghostly footprint in the starlight, yet the most profound question about these lonely worlds is what might exist on them. Cut off from the energy of any sun, their surfaces would be frozen wastelands, but beneath a thick crust of ice, heated by the slow radioactive decay in their cores, vast global oceans could persist in liquid form. Imagine a world of perpetual night where the only warmth comes from within, and the only light in the sky is the faint, unchanging tapestry of the Milky Way. In such a hidden sea, bathed in absolute darkness, could life somehow find a way? Around hydrothermal vents on Earth's ocean floors, entire ecosystems thrive without any sunlight, powered solely by chemical energy. A rogue planet could offer a similar dark refuge, a submarine oasis sailing the galaxy in total silence, potentially harboring life forms that have never known a sunrise. Far beyond the orbit of Neptune, in the cold, deep freeze of our solar system's outskirts, lies a ring of icy remnants known as the Kuiper Belt. This is the solar system's final frontier, a vast junkyard of frozen worlds and building blocks left over from the planet's formation. But this distant realm holds a sharp, unsettling boundary that astronomers call the Kuiper Cliff. Our models of solar system formation predict a smooth, gradual decline in the number of objects as you move further out. Instead, what we find is a dramatic and sudden drop-off, as if someone built a cosmic wall. Past a certain distance, the expected thousands of small, icy bodies simply vanish. The population of objects plummets, creating a stark edge to this frozen belt that defies all logical explanation. It is as if you were walking through a dense forest only to find it abruptly ends at a perfectly straight, invisible line. So what could have carved this mysterious boundary? The most compelling and thrilling hypothesis points to the gravitational influence of a hidden world. Astronomers propose that a yet undiscovered planet, a so-called Planet 9, could be lurking in the profound darkness far beyond the Kuiper Belt. This would not be a small, rocky world, but a super-Earth, a planet several times more massive than our own, on a tremendously long and tilted orbit that takes thousands of years to complete. The gravitational pull of such a colossal unseen object could be acting like a cosmic shepherd. As it travels its immense, lazy loop, its gravity would violently interact with the icy bodies in the outer Kuiper Belt, either flinging them inward toward the sun hurling them out into interstellar space or throwing them into orbits so steeply tilted that they escape our surveys. This gravitational bullying would effectively sweep a vast region of space clean, creating the very cliff we observe. The hunt for this phantom planet is one of the great modern quests in astronomy. Its signature is not light, which it would reflect only faintly from a distant sun, but its gravitational disturbance on the orbits of other distant objects. Several small, icy worlds already discovered out there have bizarre, clustered orbits that seem to be herded by something large. Finding Planet 9 would be a monumental discovery, rewriting the story of our own solar system and solving the riddle of why the outer darkness feels so strangely and suddenly empty. Even the most precisely planned journeys can be haunted by a phantom force. As the Pioneer 10 and 11 spacecraft sailed into the outer solar system, mission controllers noticed something deeply wrong. Both probes were experiencing a tiny, unexplained deceleration, a constant, minuscule tug backward as if an invisible hand was gently applying the brakes. This was the Pioneer anomaly. For decades, this subtle drift defied all explanation. It was a whisper of a problem, a deviation so small it seemed insignificant, yet it persisted across billions of miles of empty space, gnawing at the foundations of orbital mechanics. Scientists launched an exhaustive detective hunt, considering every possibility. Was it the gravitational pull of an unseen, distant planet? Was it the drag from a faint, undetected interstellar dust cloud? Could it be a sign that our understanding of gravity itself, Einstein's theory of general relativity, was subtly incorrect in the deep, cold void? The quest for an answer prompted a rigorous re-examination of physics itself, with some even proposing exotic new forces or modifications to the laws of gravity. The solution, when it finally came, was not from the depths of space, but from the spacecraft's own engineering. The culprit was heat. The plutonium power sources onboard the Pioneers were constantly emitting heat, and this thermal radiation was not escaping uniformly. A tiny, anisotropic push from this radiated heat, preferentially leaking from one side of the boxy spacecraft, was enough to create the faint, consistent deceleration. It was a lesson in humility, a reminder that even the ghost in the machine can be a mundane, if incredibly subtle, technical effect. Yet the anomaly's legacy endures. It stands as a classic example of how a deep space mystery, no matter how small, can captivate the scientific imagination and force us to question everything we think we know, proving that the greatest puzzles are sometimes hidden in the smallest details. While we grapple with phantom forces in our own solar system, an invisible rain of atomic shrapnel constantly bombards our planet from the depths of the galaxy. These are cosmic rays, not rays of light, but a torrent of high-energy particles, primarily protons and atomic nuclei, screaming through space at nearly the speed of light. They are the shrapnel from the universe's most violent events, and their origin story is one of our galaxy's greatest detective mysteries. We know some of these particles are launched by the explosive deaths of massive stars. When a supernova detonates, it acts as a natural particle accelerator, its colossal shock waves flinging atomic fragments across immense distances. Yet this explanation only solves part of the puzzle. The very highest energy cosmic rays, particles carrying millions of times more energy than anything produced in our most powerful particle colliders, have no known source. Their staggering power points to cosmic accelerators of almost unimaginable ferocity, far beyond the capabilities of a typical supernova. So what cosmic engines are capable of hurling single particles with such unbelievable force? The prime suspects are the most extreme objects in the universe. Theorists point to the violent environments around supermassive black holes, where matter spiraling into the abyss could be torn apart and energized to these incredible levels. The furious jets screaming from active galactic nuclei or the intense magnetic fields of rapidly spinning neutron stars are also capable candidates. but identifying the true culprit is incredibly difficult, and the reason lies in their journey. Cosmic rays are not neutral travelers. They are electrically charged particles, which means they do not travel in straight lines. As they cross the galaxy, they are constantly deflected and bent by the tangled magnetic fields that permeate interstellar space. Imagine trying to trace a single, ricocheting bullet back to the gun that fired it after it has bounced through an endless hall of mirrors. That is the fundamental challenge astronomers face. A cosmic ray detected here on Earth could have begun its journey anywhere in the galaxy, its original path scrambled beyond recognition. To cut through this confusion, scientists have built enormous observatories like the Pierre Auger Observatory in Argentina, which uses thousands of detectors spread over an area the size of Rhode Island. Instead of trying to catch the particles directly, which is often impossible, Auger watches for the secondary effects. When an ultra-high-energy cosmic ray slams into the top of our atmosphere, it creates a spectacular cascade of billions of secondary particles, a fleeting shower that spreads out like a giant, invisible umbrella. By studying the footprint and the faint fluorescent glow of these air showers, physicists can work backward to estimate the original particle's energy and its rough direction of arrival. It is a painstaking process of cosmic forensics, piecing together the clues from the aftermath of a single subatomic impact. With every mysterious ultra-high-energy particle that strikes our atmosphere, we are reminded that our galaxy is filled with invisible, natural accelerators of awesome power, their identities still hidden behind a maze of magnetic fields. The hunt for invisible particles and phantom planets leads us to a more personal cosmic loss. We are quite literally missing pieces of ourselves. Based on our most precise calculations of the Big Bang, scientists can predict exactly how much normal matter, the kind that makes up every star, planet, and person, should exist in the universe. This ordinary stuff is called baryonic matter. Yet when we add up everything we can actually see and detect, from the most brilliant galaxy to the faintest interstellar gas cloud, we come up dramatically short. A staggering 30 to 40% of all the atoms that should be there are simply gone. This is the missing baryon problem, and it is a profound embarrassment. It is not dark matter we are looking for this time, but the very fabric of our own reality, the building blocks of everything familiar, and half of it has vanished without a trace. So where did it go? The leading theory paints a picture of a universe laced with ghostly threads. Between the great clusters and walls of galaxies lies the cosmic web, a vast filamentary structure of dark matter that acts as a skeleton for the cosmos. Theorists propose that the missing baryons are hiding there, not in dense clumps but spread out as an incredibly thin, superheated gas. This is not a gentle mist. This intergalactic medium is a searing plasma with temperatures reaching millions of degrees. Gas this hot and this diffuse is nearly impossible to see. It does not glow in visible light, and it is too thin to cast a clear shadow. Finding it is like trying to map a fine, invisible fog by the faint heat it radiates on a summer night. Astronomers have had to develop ingenious methods to hunt for this phantom material. They search for subtle distortions it imprints on the cosmic microwave background, the leftover heat from the Big Bang. Or they use powerful X-ray telescopes to look for the faint, specific signature of highly ionized oxygen atoms as this ultra-hot gas absorbs the light from brilliant, distant objects called quasars. It is a bit like trying to find a clear, colorless thread by watching how it slightly warps the view of a bright light shining from miles behind it. Slowly, painstakingly, this evidence is mounting, suggesting that the missing matter has been here all along, woven into the very architecture of space, a pervasive, seething ocean in which all galaxies swim. Solving this mystery is crucial, for it would finally complete the inventory of our own cosmic ingredients, confirming that the ordinary world we know is not lost but simply hiding in plain sight. Our most fundamental story of creation holds a single, glaring flaw, a chemical mystery written in the light of the universe's oldest stars. The standard model of Big Bang nucleosynthesis is a triumph of modern cosmology, a set of equations that describes how the first atomic nuclei forged themselves in the fiery aftermath of the universe's birth. For the most abundant elements, its predictions are stunningly accurate. The observed amounts of hydrogen and helium throughout the cosmos match the model's calculations almost perfectly, a powerful confirmation that we understand the broad strokes of those first few minutes. But for one seemingly minor element, the math falls apart. The model tells us there should be about 3 times more lithium-7 in the ancient universe than what we actually find. When we look at the oldest stars in the Milky Way, celestial fossils that formed from nearly pristine material, their atmospheres contain only a third of the lithium that our premier theory of cosmic origins says they should. This is the cosmological lithium problem. It is a small discrepancy with enormous implications, a crack in the foundation of our understanding of the universe's first moments. How do we solve a puzzle that is over 13 billion years old? One possibility is that our understanding of stellar physics is incomplete. Perhaps these ancient stars have internal processes, slow-burning nuclear reactions deep in their cores or specific mixing patterns in their atmospheres that gradually destroy lithium over their immensely long lifetimes. We know that some stars do destroy lithium, but the question is whether this can account for the universal shortage we see across so many different ancient stars. The other, far more radical possibility is that the fault lies not with the stars, but with the Big Bang model itself. Could there be unknown particles or forces at play in the early universe that altered the nuclear reactions? Some physicists have proposed exotic ideas, like the existence of a previously unknown type of neutrino that could have interacted with the primordial soup, skewing the delicate nuclear chain reaction that produced lithium. Others have looked to theories beyond the standard model of particle physics, suggesting that hypothetical particles like actions or supersymmetric particles could have absorbed neutrons at a critical moment, effectively starving the nuclear processes that create lithium-7. Yet none of these elegant solutions has provided a definitive answer. The lithium problem endures as a quiet but persistent thorn in the side of cosmology, a reminder that even our most successful and beautiful models of the cosmos might still be missing a crucial piece of the puzzle. The invisible dark matter halo surrounding our galaxy is far from a perfect, symmetrical sphere. For decades, that was the simplest assumption, a gentle, cloud-like cocoon enveloping the bright spiral disk. But the ghostly skeletons of devoured galaxies are now telling a different story. Across the sky, we see the shredded remains of small galaxies that ventured too close to the Milky Way. Their stars have been torn into long, shimmering rivers that wrap around us, streams like the one torn from the Sagittarius dwarf galaxy. These stellar rivers do not flow in random patterns. They follow the subtle, invisible contours of the dark matter halo's gravity, and their paths are telling us the halo's shape is all wrong. It appears to be lumpy, uneven, and significantly tilted compared to the flat plane of our galaxy. Some measurements even suggest it is triaxial, shaped less like a ball and more like a colossal cosmic rugby ball. How do you map something you cannot see? You watch how everything else moves within its grasp. The orbits of the small satellite galaxies that still dutifully circle the Milky Way also hint at this distorted gravitational landscape. Their paths are not what we would expect if they were orbiting within a calm, spherical cloud. Instead, their motions suggest they are tracing the lines of force around a lopsided, clumpy, and dynamically active structure. This is not a serene halo. It is a relic of violence, a fossil record of our galaxy's growth through cannibalism. Every small galaxy it has consumed has left a gravitational scar, a lump of dark matter that has not yet smoothed itself out. The precise shape of this dark matter halo is not just a matter of cosmic cartography. it holds the key to understanding what dark matter actually is. Certain theoretical candidates for dark matter, like cold, slow-moving particles, would form smooth, spherical halos. Others, like warmer, faster-moving particles, would create more lumpy and elongated structures. By meticulously measuring the true shape of our galaxy's invisible skeleton, we are indirectly testing the fundamental properties of the universe's most mysterious substance. The warped halo is a silent witness, its form a direct challenge to our theories, forcing us to question the very nature of the ghost that holds our galaxy together. These stellar corpses are cosmic powerhouses of unimaginable ferocity. Magnetas are a rare breed of neutron star, the collapsed core of a giant star, but they possess a unique and terrifying property. Their magnetic fields are the strongest in the known universe, so powerful they defy human comprehension. To put it in perspective, a magneta's magnetic field is 1 trillion times stronger than Earth's. If one were to magically appear halfway between the Earth and the Moon, its sheer magnetic force would be strong enough to strip the data from every credit card on our planet. These fields are not static, they are dynamic, twisted, and under immense stress, and when that stress becomes too much, the star's rigid crust suddenly cracks. This event is a starquake, a seismic shift on a stellar scale. The energy released is staggering. In a fraction of a second, a single starquake can unleash more energy than our Sun will emit over 100,000 years, all in a blinding flash of gamma rays and X-rays. The central mystery is how such an impossibly intense magnetic field is even created and sustained. The leading theory points to a perfect storm during the star's violent birth. When a massive star collapses into a neutron star, its core is compressed into a sphere only about 12 miles across. This process, known as the dynamo effect, could amplify a regular neutron star's magnetic field to magneta levels, but only if the infant star is spinning at a breakneck speed. It is this rapid rotation, combined with the chaotic churning of superheated plasma in its first few seconds of life, that might twist and wind the magnetic field into a state of such extreme power. And this brings us back to a mystery we encountered earlier. The detection of a fast radio burst from within our own galaxy was traced directly to an active magneta. The connection is compelling. It suggests that the colossal magnetic tantrums of these objects, the shudders and quakes in their crust, can indeed launch those incredibly brief, powerful radio signals across interstellar space. Yet, this solution only deepens the enigma. If magnetas are responsible for some fast radio bursts, can they account for all of them, especially the ones that repeat from distant galaxies? The internal physics of a magneta remains a theoretical frontier, a place where matter is squeezed into exotic states and magnetic fields rule supreme, making these objects some of the most volatile and mysterious magnets in the cosmic zoo. But what if the very architecture of our galaxy creates safe neighborhoods and deadly wastelands? The concept of a galactic habitable zone suggests that life, especially complex life, might only be possible within a specific, narrow band of the Milky Way. This is not about a star's orbit, but our solar system's place in the grand spiral. To be suitable for life, a region must strike a delicate balance between two cosmic extremes. It must be far enough from the chaotic galactic center to avoid catastrophe. The inner galaxy is a violent place packed with stars. The frequency of nearby supernova explosions there would be devastating. A close enough supernova could strip a planet of its protective ozone layer, bathing its surface in lethal ultraviolet radiation from its own sun, effectively sterilizing worlds that might have otherwise been fertile. Yet, a life-bearing system cannot be too far out in the galactic suburbs either. The outer reaches of the Milky Way's disk are impoverished in what astronomers call metals, the heavy elements forged in the hearts of stars and scattered by those very supernovae. These elements, everything heavier than hydrogen and helium, are the essential building blocks for rocky planets like Earth. Without a sufficient abundance of iron, silicon, and oxygen, a planetary system would consist only of gas giants and icy bodies, with no solid, terrestrial worlds upon which life could gain a foothold. This creates a cosmic sweet spot, a relatively narrow ring within the galactic disk where the conditions are just right. Our own solar system orbits within this privileged zone, about halfway between the vibrant but dangerous core and the sparse, barren outskirts. This leads to a profound and haunting question. Is complex life confined to this specific annular band within the Milky Way? If so, the number of potential civilizations could be far smaller than we might hope. It paints a picture of a galaxy where life is not just rare, but also geographically isolated, confined to a single, luminous street in a vast metropolitan sprawl. The mystery deepens when we consider time itself. The galactic habitable zone is not static. As the Milky Way evolved, producing more heavy elements over billions of years, this life-friendly ring has likely migrated and expanded. This means that planets forming at different times in different locations may have had their chance at life come and go. We are left to wonder if we are not just in the right place, but also at the right time in our galaxy's long and turbulent history. This emptiness on a cosmic scale is almost beyond comprehension. Far beyond the borders of our own Milky Way, in the constellation of Bootes, lies a sphere of near-nothingness so vast it could swallow thousands of galaxies whole. This is the Bootes Void, a cosmic cavern hundreds of millions of light-years across where the universe seems to have simply forgotten to put anything. In a cosmos we believe is built on a grand, web-like structure of galaxies and clusters, this void is a staggering anomaly. If you were to place yourself at its center, the night sky would be profoundly, terrifyingly dark, with only a handful of faint, lonely galaxies punctuating the abyss. How does something this large become so empty? Our best models of the universe's evolution, which beautifully explain the clumping of matter into galaxies and superclusters, struggle to account for a void of this magnitude. It is like finding a single, perfectly spherical bubble 1,000 miles wide in the middle of a dense ocean. The sheer scale of the emptiness suggests that the processes which distribute matter are not just random, but might be influenced by forces or conditions we do not yet fully understand. So what could have carved out this immense pocket of nothing? One theory points to the coalescence of smaller voids. Over billions of years as the universe expanded, smaller underdense regions might have merged, their emptiness feeding on itself to create a single colossal void. Another, more exotic idea involves the influence of dark energy, the mysterious force accelerating the universe's expansion. Perhaps in this region, dark energy acted with unusual ferocity, pushing matter apart before it could ever coalesce into galaxies, creating a cosmic desert. The existence of the Bootes Void forces us to confront a humbling possibility. What if our own Milky Way is not in a typical part of the universe? Is it possible we are also residing in a vast, underdense region, a local void that we have simply not yet recognized because it is all we have ever known? Some astronomers are now gathering evidence that suggests exactly that. We may be living in a local bubble, a region of space less densely packed with galaxies than the cosmic average. This would mean our entire view of the cosmos is skewed, that the universe beyond our local neighborhood is far more crowded and structured than we can perceive from our relatively quiet corner. The void next door is a silent reminder that the universe's greatest structures are not just the brilliant clusters of light, but also the profound, echoing absences between them. Our journey into the void now brings us to the very edge of our solar dominion, to a realm of pure theory and shadow. The Oort cloud is the final frontier of our sun's gravitational influence, a vast spherical shell of icy planetesimals believed to encase our entire solar system like a colossal, distant fog. This is not a place you can see or visit. It is a hypothetical structure, a necessary idea born from the behavior of comets, yet it has never been directly observed by any telescope. We infer its existence from the long-period comets that occasionally plunge into the inner solar system from every conceivable direction. These icy wanderers, with orbits lasting thousands or even millions of years, must originate from somewhere, and the Oort cloud is the only explanation that fits. It is the solar system's ultimate deep freeze, a reservoir of pristine, ancient ice left over from the formation of the planets. The challenge of proving its existence lies in the sheer, mind-numbing distance. The inner edge of this cloud is thought to begin about 2,000 times farther from the Sun than Pluto, stretching outward for another light year or more. At such ranges, the objects within are not just dark, they are virtually undetectable. They reflect almost no sunlight, and their own heat signature is lost in the cosmic background. Spotting one would be like trying to see a single, black snowball in the pitch darkness of a cavern miles wide. This immense distance also means these icy bodies are only loosely bound to the Sun. They drift in a gravitational twilight zone, easily disturbed. The gentle tug of a passing star, the gravitational nudge from a galactic tide, or even the wake of a giant molecular cloud can dislodge one of these frozen relics, sending it on a million-year fall toward our Sun. But the cloud's isolation and vastness lead to even more tantalizing possibilities. Could this distant shell be a cosmic crossroads, a place where our solar system captures visitors from other stars? Astronomers theorize that the Oort cloud might be littered with interstellar interlopers. Objects like the strange, cigar-shaped Oumuamua could be just one of many such travelers temporarily residing there, caught by the Sun's gravity during its journey through the galaxy. Even rogue planets, those dark nomadic worlds we discussed earlier, could be lurking in this profound darkness, captured and hidden in the Sun's distant grasp. The Oort cloud is therefore more than just a source of comets. It is a frozen archive of our solar system's earliest days and potentially a secret repository for cosmic drifters from across the Milky Way, all hiding in the perpetual twilight at the very edge of our light. These cosmic lighthouses are beginning to flicker in ways we cannot explain. Cepheid variable stars have long been the trusted mile markers of the universe. These stars rhythmically brighten and dim, and the very clockwork of their pulsation is directly tied to their true, intrinsic brightness. By measuring the period of their pulse, astronomers can determine exactly how luminous they are, and by comparing that to how dim they appear from Earth, we can calculate their distance with remarkable precision. They are the foundation upon which we have built our cosmic distance ladder, the essential first step that allows us to measure the scale of our galaxy and the expansion of the entire universe. Yet, some of these crucial stars are now behaving strangely. A number of Cepheids have been caught changing their rhythm. Their pulsation periods are subtly shifting, speeding up or slowing down in ways that our best stellar models fail to predict. Their brightness, too, can show unexpected variations, flickering with an inconsistency that should not be possible for such reliable standard candles. Imagine if the mile markers on a highway began to randomly shift their positions. Your entire map of the journey would become unreliable, throwing every calculation of distance and speed into question. This is precisely the crisis these anomalous Cepheids are creating. The implications ripple outward to the very edge of cosmology. The Hubble constant, the number that describes how fast the universe is expanding, is measured using a chain of cosmic distance markers, and Cepheids are the most critical rung on that ladder. If our understanding of their true brightness is flawed, then our measurement of the expansion rate is fundamentally uncertain. This single mystery lies at the heart of a major conflict in modern astronomy, the so-called Hubble tension, where different methods of measuring the universe's expansion yield conflicting results. Could these misbehaving stars be the source of the discrepancy? The hunt for an answer is leading scientists to reconsider the inner lives of these giants. Perhaps they are experiencing enhanced mass loss, shedding their outer layers and altering their internal structure in unpredictable ways. Maybe they exist in binary systems where the gravitational tug of an unseen companion star perturbs their steady rhythm. Or their internal dynamics could be more complex than we thought, with convective zones and magnetic fields interacting in ways our models have not yet captured. Every unexplained pulse from these distant lights is a challenge to our cosmic cartography, a quiet signal that the map of the universe we have so carefully drawn might still need fundamental revision. The reliable pulse of Cepheid stars gives way to a profound and nearby silence. Just 1,500 light-years away, in the familiar constellation of Orion, lies a cosmic cavity so immense it could swallow our entire local stellar neighborhood. This is the Orion Eridanus superbubble, a gaping void in the interstellar medium spanning hundreds of light-years. Imagine a sphere of near-perfect vacuum, a region of incredibly low-density gas where space itself seems to have been scoured clean. This is not an empty void like those between galaxies, but a hollowed-out chamber within one of the Milky Way's own bustling spiral arms. It was not carved by a single cataclysm, but by a sustained, violent symphony of stellar creation and destruction. The culprits are the brilliant, short-lived giants of the Orion OB1 Association, a family of massive stars. These titans do not live quiet lives. They burn through their nuclear fuel in a frenzied rush, blasting the space around them with powerful stellar winds, a constant hurricane of charged particles. And when their brief lives end, they do not fade away, they explode. Multiple supernovae have detonated within this region over millions of years, their collective shockwaves acting like a team of cosmic bulldozers. These forces have pushed the surrounding gas and dust outward, piling it up into a dense, glowing shell that we see as the arc of Barnard's loop, a faint, eerie ribbon of light that traces the bubble's edge. The central mystery is not its existence but its complexity. Precisely mapping the full, three-dimensional shape of this superbubble is incredibly difficult. We are inside its structure, looking out through its tangled walls, trying to discern the architecture of the cavern we inhabit. How exactly did these countless stellar winds and supernova blasts combine their energy? Did they work in concert or in a chaotic sequence of eruptions? This is the puzzle of feedback, a fundamental process that shapes all galaxies. The death of stars clears away the cosmic raw material, preventing new stars from forming in that cleared zone, while simultaneously compressing the surrounding gas to trigger the next generation of stars in the shell itself. It is a cycle of cosmic death and rebirth on a colossal scale, and this nearby superbubble is our front row seat to understanding how the galaxy constantly remodels itself, one violent breath at a time. The echoes of a stellar cataclysm still linger remarkably close to home. Known as the Monogem Ring, this vast, ghostly nebula is a faint circle of X-ray emitting gas that spans over 20 degrees in our sky, the aftermath of a supernova that detonated a mere 100,000 years ago. On a cosmic timescale, this is a recent event, a stellar explosion that occurred at a time when early humans were already walking the Earth, and it happened relatively nearby, only about 800 light-years away. That proximity makes it one of the closest known supernova remnants to our solar system, a titanic blast whose shockwave would have passed through our corner of the galaxy, potentially affecting the heliosphere that protects our planets. The ring itself is the expanding shell of that ancient explosion, a bubble of million-degree gas that glows not in visible light, but in high-energy X-rays, a visible testament to the violence that forged it. Yet, the central mystery of the Monogem Ring is not the blast itself, but what was left behind. Every supernova is expected to leave a compact core, either a neutron star or a black hole. Here, the prime suspect is a nearby object named Geminga, a pulsar discovered in the 1970s. Geminga is a fascinating object in its own right, a rapidly spinning neutron star that is one of the brightest sources of gamma rays in the sky, yet it is virtually invisible in other wavelengths. The name itself is a play on words from the Milanese dialect meaning, "it's not there," a nod to its long period of elusiveness. But is Geminga truly the stellar corpse of the supernova that created the monogem ring? The evidence is compelling, but not yet conclusive. The pulsar's estimated age and its motion through space seem to align with the remnant, as if it is fleeing the scene of the crime. However, definitively linking this particular pulsar to this specific supernova remnant has proven to be a complex astrophysical puzzle. Studying structures like the monogem ring is crucial because they are the galaxy's great recyclers. The supernova that created it did not just destroy a star, it forged and scattered the heavy elements that were cooked in its core and during the explosion itself. Atoms of iron, oxygen, silicon, and carbon were flung out into the void, enriching the interstellar medium. This cosmic debris, this stellar ash, will one day collapse into new clouds of gas and dust, forming the next generation of stars, planets, and perhaps even life. The ring is a fossilized moment of both destruction and creation, a permanent reminder that the very atoms that make up our world were once forged in the heart of a star that no longer exists. Our galaxy is not just drifting in a random sea of darkness. It is part of a current, a flow that may be guided by the largest structures we have ever discovered. Far beyond the Milky Way, astronomers have mapped a cosmic formation of such staggering scale it defies belief. A colossal filament of galaxies known as the Hercules Corona Borealis Great Wall. This is not merely a cluster of galaxies, but a gravitationally bound ribbon of superclusters, a vast wall stretching over 10 billion light-years from end to end. To grasp its size, consider that the entire observable universe is only about 93 billion light-years across. This single structure occupies more than a tenth of that distance, a thread in the cosmic web so immense it should not, by our best theories, exist. This discovery strikes at the heart of a fundamental assumption in cosmology, the cosmological principle. This principle states that on a sufficiently large scale, the universe should look roughly the same in every direction and from every location, a homogeneous and isotropic cosmos. The existence of the Great Wall and other structures like it directly challenges this idea. How can the universe be considered smooth and uniform when it contains such glaring, colossal concentrations of matter? It is like claiming the ocean is a perfectly uniform fluid while ignoring the existence of entire continents. This forces us to question whether our view from Earth is representative, or if we are simply living in a quieter, less dense neighborhood, blind to the true metropolitan centers of the cosmos. The gravitational pull of such a massive nearby wall must be immense. While we are not inside it, its sheer mass could be subtly influencing the motion of our entire local group of galaxies, including the Milky Way. We already know we are being pulled toward the great attractor, but that force itself might be just a local eddy in a much larger river, a current ultimately set in motion by the titanic gravity of the Hercules Corona Borealis Great Wall. It is a humbling thought that the grandest motions of our galaxy through the void might be orchestrated by an architecture of matter so vast we can barely comprehend its dimensions. These particles carry energies that defy belief, millions of times greater than anything our most powerful machine, the Large Hadron Collider, can produce. They are so powerful that physicists, upon detecting the first one, could only exclaim, "Oh my God!" An "oh my God" particle is a single subatomic traveler, a proton or atomic nucleus, moving with so much kinetic energy it feels like getting hit by a major league fastball, but all that force is packed into a single, minuscule particle. The sheer existence of such a thing pushes the very limits of known physics. What kind of cosmic engine could possibly impart such an unbelievable kick? We know of natural particle accelerators in space, like the shock waves from supernova explosions, but they are simply not powerful enough to explain this. A supernova would be like a firecracker compared to the cosmic cannon required to launch an "oh my God" particle. So what cosmic events possess such unimaginable violence? The prime suspects are the most extreme environments in the universe. Theorists look to the cores of active galaxies, where supermassive black holes devour entire stars and launch jets of plasma at near light speed. Perhaps a particle could surf these relativistic jets, gaining immense energy from the intense magnetic fields. Another candidate is the cataclysmic collision of two neutron stars, or a gamma-ray burst, the single most energetic explosion since the Big Bang itself. These events have the raw power, but the mystery deepens because when we trace the rough paths of these ultra-high-energy cosmic rays back into the sky, they do not neatly point back to any of these known spectacular sources. The sky should be lit up with the birthplaces of these particles, but instead we find a confounding emptiness. The sources remain completely unidentified, hidden behind the same magnetic maze that scrambles their path. This leaves a haunting possibility on the table. Could these particles be the signature of something entirely new, a physical process or a celestial object we have not yet even dreamed of? Every one that strikes our atmosphere is a messenger from the universe's most powerful and secret laboratories, carrying a coded message about forces that lie beyond our current understanding. This central bar of stars is the great engine at the heart of our galaxy. Unlike the graceful spiral arms that unwind from it, the bar is a dense, elongated structure of millions of stars, all moving together in a slow cosmic dance. It rotates as a single, rigid body, a colossal stellar railroad turning through the galactic core. This rotation is not just a spectacle, it is a fundamental force that shapes everything within the inner Milky Way. The bar's immense gravity acts like a giant paddle in a river of stars and gas, stirring up the inner galaxy and creating powerful gravitational shocks. These shocks push and compress the vast clouds of hydrogen gas that drift inward, triggering violent episodes of star formation. The bar essentially funnels fuel toward the galactic center, feeding the supermassive black hole and creating the intensely bright stellar nurseries we observe there. Yet for such a pivotal structure, we know surprisingly little about its precise characteristics. Its exact size is a subject of ongoing debate because we are embedded within the disk and cannot get a clear top-down view. Determining its rotation speed is equally challenging, as we must measure the subtle, collective motion of billions of stars obscured by intervening dust clouds. How does this rotating bar connect to the spiral arms themselves? Are the arms trailing behind the bar's ends like cosmic ribbons, or are they independent structures that the bar influences through its gravitational wake? The answers to these questions are vital. The galactic bar is the primary driver of what astronomers call secular evolution, the long-term, internal changes that reshape a galaxy over billions of years. By understanding its dynamics, its true size, and its rotation, we can create a more accurate model of our galaxy's past and future. We can predict how material will flow, where new stars will ignite, and ultimately, how the entire magnificent structure of the Milky Way will evolve over cosmic time. Even as colossal structures dictate the grand motions of galaxies, some of the most profound clues to cosmic history come from the smallest and strangest of them all. Scattered across the sky are tiny, brilliant objects known as green pea galaxies. These are not majestic spirals, but dwarf galaxies so compact they appear as small, fuzzy green dots in telescope images. Their striking color is not from stars, but from the gas within them. They are undergoing such an explosive, extreme burst of star formation that the intense ultraviolet light from all their newborn, massive stars is causing the surrounding oxygen gas to fluoresce with a vivid green glow. It is a cosmic neon sign advertising a riot of stellar birth on a miniature scale. These tiny powerhouses are creating new stars at a rate that is staggeringly high for their small size, a ferocity that makes them invaluable to astronomers. They are living fossils, nearby analogues of the very first galaxies that ignited in the early universe. In that ancient era, the cosmos was filled with a fog of neutral hydrogen gas. The first stars and galaxies had to burn through this fog, their intense radiation blasting the hydrogen atoms apart in a process called reionization, ultimately clearing the universe and making it transparent to light as we see it today. Green pea galaxies give us a front-row seat to this pivotal epoch. By studying their intense radiation and how it interacts with their own gas, we can understand the mechanics of how the early universe was transformed from opaque to clear. They are a crucial missing link, showing us how small, energetic galaxies could have provided the collective energy needed to reionize the entire cosmos. Beyond the green peas, astronomers have discovered even smaller, denser objects nicknamed blueberry galaxies. These are similar in their frantic star formation, but appear even bluer and more compact, pushing the limits of what we consider a galaxy. Their existence raises fundamental questions about galactic evolution. Are these tiny, ferocious systems a distinct and short-lived phase in a galaxy's life, a final, glorious burst of star formation before they settle down or fade away? Or are they the pristine building blocks from which all larger galaxies were eventually assembled, the elementary particles of the cosmic web? Their peculiar properties and place in the broader family of galaxies remain an area of intense investigation, a reminder that sometimes the biggest secrets of the cosmos are held within its smallest and greenest inhabitants. The ultimate destiny of our galaxy is written in a slow, cosmic dance that has already begun. In roughly 4.5 billion years, the Milky Way will cease to exist as we know it. Our nearest large galactic neighbor, the Andromeda galaxy, is currently hurtling toward us at a speed of around 250,000 miles per hour. This is not a chance encounter, but an inevitable merger, a gravitational embrace from which neither galaxy can escape. The result of this colossal collision will be a new, blended galaxy that astronomers have nicknamed Andromeda. What would this cosmic event look like from a hypothetical Earth? The night sky would transform over millions of years. The approaching Andromeda galaxy would grow from a faint smudge into a brilliant, sprawling tapestry of light, eventually filling half the sky. Yet, despite this spectacular celestial show, the actual collision would be remarkably peaceful. The vast distances between stars mean that direct stellar impacts are incredibly unlikely. Our solar system would probably be flung onto a new, wild orbit within the merged galaxy, but the Sun and its planets would physically survive the encounter. The real drama will unfold at the galactic cores. The supermassive black holes that currently anchor both the Milky Way and Andromeda will begin a gravitational tango, slowly spiraling toward one another over billions of years. As they draw closer, their immense gravity will fling stars away in a cosmic slingshot, clearing a vast region around them. Eventually, they will merge in an event of unimaginable power, shaking the very fabric of space-time and sending ripples of gravitational waves across the universe. The new galaxy born from this union will be an elliptical blob, a vast sphere of stars without the beautiful spiral arms we see today. The era of rapid star formation, fueled by the collision's shockwaves, will eventually cease. One by one, the remaining stars will burn through their fuel. Massive stars will explode, while smaller, longer-lived stars like red dwarfs will slowly cool and fade. Over trillions of years, the lights will literally go out. Andromeda will evolve into a dark, cold sea of stellar corpses, populated by black holes, neutron stars, and failed stars known as brown dwarfs, a silent monument to a vibrant past. This final transformation forces us to confront the deepest timeline of cosmic evolution, a future so distant it challenges our very perception of time and place in the universe. From the invisible scaffolding of dark matter to the final, silent twilight of Andromeda, our journey across 25 galactic mysteries reveals a universe far stranger than we ever imagined. We have navigated rivers of galaxies pulled by unseen attractors, witnessed the flicker of cosmic lighthouses that defy measurement, and stood at the edge of voids so vast they challenge our deepest principles. Each of these phenomena, from the phantom rain of oh my god particles to the secret oceans of rogue planets, is not merely a puzzle to be solved, it is a frontier. These are the burning questions that push our technology to its limits and force our understanding of physics to evolve. They remind us that the cosmos is not a static museum, but a dynamic, living entity, constantly revealing new layers of its profound and beautiful complexity. The true value of this exploration lies not in the answers we have, but in the questions that still remain. Every time we look up at the starry band of the Milky Way arching overhead, we are gazing into a realm of endless wonder, a home galaxy that still keeps its greatest secrets close. So keep looking up, keep wondering, and let us know which of these cosmic mysteries captures your imagination the most. Is it the ghostly halo of dark matter, the brief, brilliant flash of a fast radio burst, or the silent, drifting hope of life on a lonely rogue world? Share your thoughts, and together we continue the greatest adventure of all, the exploration of our magnificent and mysterious universe.